I'm Francesc Campoy, and today I'm going to be talking about Google Cloud Spin. Just to have a basic idea, how many of you know what Google Cloud Spin is? OK, how many of you have actually taken a photo with it? Only one? Wow, OK, and me too. So you're going to see what Google Cloud Spin is. It's a demo that we built, lots of fun. And the whole thing is I'm going to show you how we actually made it, with all the fails included. There were a lot of them. So the idea was, OK, so let's build the demo for GCP Next 2016, which was a month ago, actually, in San Francisco. And we had two options. We had a couple of options. We had a couple of constraints. We needed to be able to make it in 2 weeks with basically no budget, which is always fun. We're 4 people, and there was actually 3 weeks. But in the meanwhile, it was my birthday and someone else, so with holidays in the middle, lots of fun. So we decided, let's just reuse the one we already have from 2015, which is Avellana. And if you are interested, it's an Instagram clone, and it's open sourced. So you can check it out, and basically, it's a pretty simple app. It's more of an Android app more than a cloud app. But there's some image processing on the back. That's pretty cool. Then someone came with the idea. I was like, hey, slow-mo is the thing everybody does. Why don't we do slow-mo? It's like, Android does slow-mo, iOS does slow-mo. Awesome. But where's the cloud? Yeah, no. But what if we could do slower than slow-mo? What if we could stop time? And we had this idea where basically it's like, OK, so I love the Matrix, at least the first one. So what if we took all of these pictures at the same time as they do? They're using 100 cameras surrounding Containerization in the middle. And then we use all of those pictures to generate this animation that makes the effect of stopping time. I was like, that is awesome. And then I went to my manager. I was like, hey, I want to buy 100 cameras. And he was like, no. Which I understand. So how do you reduce the budget? Well, 2 ways. Instead of 100 very expensive cameras, let's reuse 20 phones we already have. So we had 20 Android phones together. And then instead of having Ken Reeves or whoever, just have me. Much cheaper, I guarantee. And this is what we did. We had 20 phones. And then we talked to our friends in Android. It was like, hey, so we want to take 20 pictures exactly at the same time over the network. And they were like, sure, try it. And that's pretty much what you get. You get a lot of 20 pictures that are around the same time, but definitely not good enough. And then we had this idea. It's like, OK, so instead of taking pictures, let's make a video. So what we do is we have a 6 seconds video. Now, that variability of when the picture is taken, it's now when the video starts, which is fine, because then we're going to use it on the movies. We're going to use that clap. And that's my animation for clap. And that's going to be the synchronization point, and then we stop the video. Cool. So once we had the idea and pretty much the concept, we create this beautiful, beautiful diagram. There's an engineering diagram. Basically shows there's a circle, there's degrees, and that's it. So 19 phones, 10 degrees, 180 degrees, everything works, we're happy. And then we send this to marketing, and they were like, yeah, it's going to look like this. And we're like, yeah, that is cool. That is much better. And that's actually how it looked like. This is the first time we did it. This is in New York. And this was really cool. And this is one of the first tries we did with the whole demo. And I hope you're going to be able to hear. There's 2 important things here. One is listen to the noise, the background noise, and also the beep. And also pay attention to what the black duct tape goes. That's my head. Yes. So the important thing is that you hear that noise, that background noise. That is part of life. There's background noise everywhere. You have to deal with it. But we need to find that noisy frame. And then from that noisy frame, we're able to extract one image, which is this image here. Then we have 19 phones. So we extract more, And then we put it together. And then we stop time, which is pretty amazing. And it looks really, really cool, taking into account that everything you need here is just a bunch of phones and writing code. So the backend architecture, how does this work? Well, we upload videos. Magically, we process them. We extract a single frame from that video. Then we put all those frames together, and we stitch them into one single animation, video or GIF or GIF. And then we display it. And this is the whole thing. Now the next step is like, sure, how do you do this? And that's the rest of the talk. So the first part is, OK, how do I tell 20 phones take a picture now at the same time? And every single one of the phones knows what's their ID, what is the picture quality that they want, all the things that you need to specify for a picture. Well, let's see actually this demo now. It's gonna give you a bigger idea of what kind of synchronization we need. This is Ray, one of the guys that helped with the demo, and you can see all the phones, and they're green. That's because they're ready to record. Then we have that tablet that said, OK, start recording. Yellow means, wait a second, I'm starting to record. Blue means I'm recording. Then Ray jumps, we press a button, and that button sends the audio through all the cables. And then we have this dashboard that's going to be showing everything that's going on. So, OK, the videos now are being uploaded. We were over conference Wi-Fi, so good luck with that. But it takes a little bit. But now, all those greens, it means that we're now extracting the frames. You can now see the frames. And once all the frames have been extracted together, we'll be able to actually stitch them together and generate the image, right? The cool thing is that this dashboard was created 2 days before the demo. And how was it possible for us to build these things so easily? It was actually because the synchronization mechanism that we used was very powerful. Almost there. Yeah, the Wi-Fi still upsets me when I see the video. I know it's going to happen, but still. There you go. The last video, it gets uploaded, extracted. We stitch everything together, and then we put it into the output bucket. And then you get Ray is about to jump. The picture was taken a little bit too early. That's actually kind of the hard part of it. OK, so we want to be able to synchronize a bunch of devices. We want real-time notifications. Start recording has to happen right now. You cannot wait for if you wait for too long, the video is only 6 seconds. You will miss it. We need to be able to have diverse clients. We've seen the Android phones, but we also have things like our web dashboard needs to be able to get that data. And then our extractors, our stitchers, and all the other workers need to be able to also modify the states, the status. And then also, I don't want to be pulling data all the time. Is this frame ready? Is this frame ready? No, I just want to say, just let me know when this is ready. And obviously, we use Firebase. Why did we use Firebase? Well, because this console is pretty amazing. The fact that I can see what's going on in my system before building any dashboard, for me, that's a huge thing, especially when you're debugging and you have weird bugs like, oh, someone misspelled his name on this field. Things happen. So the fact that you're able to see it here so easily is pretty powerful. It has 3 main clients for JavaScript, iOS, and Android. And in Java, this is a part of the code that we have to be able to send the status of the current camera. So we're saying camera number 1 is ready to record, and it's getting input from external mic or internal mic. We actually care about that a lot. So when we show the state, external mic is green, internal mic is yellow, and if something fails, it's red. So this from the tablet, you're actually able to see the status of all the phones. You're also able to modify the ISO for the pictures, which is very cool, because imagine if you had to change the ISO in every single phone separately. We did that once, only once. And as I said, we have these three library clients. But my favorite API, which one do you think it is? REST API, because I'm a cloud man. And the cool thing about REST API is then you can build things on top of it. And I'm also a Gopher. So you can actually write in Go things like this that will modify Firebase from Go. And this works perfectly, and it's super nice to use. So I was very happy with this. The stitcher is written in Go completely, and it uses Firebase. The Python, so Extractor is written in Python. It also uses the API, but it uses the bare REST API without any client library on top. So with Firebase in the middle, how does this work? Well, we upload the videos, we tell Firebase, and we tell the dashboard. We extract the frames, we tell Firebase, and we tell the framework, the dashboard. We stitch all the frames, we tell Firebase, and then we display the result, and everything is in Firebase. So the thing is that that dashboard was created like 2 days before the demo. Why? Because all the data was already there. Everything we had to do was just basically just map it into some cute way of displaying it. That was very powerful. So media storage. Let's talk about how we store all of those videos. So we have 3 places where we have to store videos, in media in general. We have our videos, we have the frames, and then we have the generated animations. And there's a couple of requirements that we have on this. First of all, these are videos, and every single one of those videos is between 10 and 20 megs, depending on what you're actually doing. But what if we wanted to do extra things? Or what if our animation starts to get pretty cool, pretty crazy, and we start to have like gigabytes of video? Maybe terabytes? Nah, terabytes now. But what if we had terabytes of data? We need to plan for that. Also, we want to be able to say, as soon as a frame has been extracted and I put it in the disk, I want anyone to be able to go and read it. I don't want something that was like, put it there, and then I read it directly, and I was like, wait, what? And then 2 seconds later, oh yeah, the file was there, sorry. That is what we call eventual consistency. I do not want that for this system. And then finally, it'd be really sweet if every single time there's a new file, a new video that has been uploaded, I could get a notification from it. We have 3 options to store data on Google Cloud Platform. There's actually a 4th one, Cloud Big Table. I will not mention it other than it is very, very, very big table. So if your tables are not that big, maybe don't even consider it. But we have data store. Data store is for structured data that is not relational. Our data is not structured, it's a video. No, we're going to do that. SQL is structured data, again, that is relational. Again, we have unstructured data, we cannot use it. The last one, cloud storage. What do we use cloud storage for? Everything else. You can store cat videos and GIFs and whatever you want. A little bit of the marketing aspect of Google Cloud Storage. You can store terabytes of data, which is way more than a GIF will ever be, I hope. It is very reliable. There's 3 flavors, and we'll see them later. But the highest availability that we provide is 99.9% availability, which is really good. And it's also replicated across many regions, which means that if for any reason a Google data center disappeared into the void, you could still not lose data, because your data is actually replicated in many data centers. And then it actually has that change notifications that we wanted. We're going to be able to get notifications every single time something happens in our storage. So the 3 flavors that I mentioned before are standard. And standard is the fastest, the most available, and all of them are exactly the same durability. Important thing, durability is, will we lose your data? And the answer is no. The durability is always to the top in every single one of them. Standard is the one that we're using because we want something that will allow us to access the information very quick and very often. If you don't need that information to be available all the time, but you want it to still be pretty quick, imagine MapReduce. You can use durable reduced availability storage. It's less available, but the durability is still there. And finally, we have nearline. And nearline, it's basically when you want to store a lot of data that you will never read until you have a bug, and then you will want to read it, and it's really important it's there. So all the durability is there, but instead of taking milliseconds to download the files that you put there, you're going to have to wait an incredible amount of seconds. So it's not hours, it's just seconds. Little bit of Android code. I'm not a Java person, so every single time I see so many types written, it's, But you first build a storage with Storage Builder. Basically, you give all the authentication and stuff like that so to be able to say, this is my storage client. Then I create a storage object that is the file that is going to be. And then with a file input stream, I will actually upload my video into the output. And what could go wrong? Exceptions? Yeah, sure. So there's some exceptions to be handled there, but it doesn't fit in the code. So this is not, just don't copy paste into production yet. Cool. So let's talk about object change notifications. Object change notifications allows us to, every single time there's a change in our bucket, we're going to get a notification set to a webhook. And you can set that up with JSUtil. That's it. You say, hey, JSUtil notification, watch this bucket, and send changes to that webhook. So now when one of my phones uploads a video, that video will generate a notification sent to my notification processing endpoint. We'll see what that is in a minute. And what is in that notification? Well, it's an HTTP post request that has a lot of things inside, but we care only about the fact there's the name and the bucket. So you get the name of the file and what happened to it. It's like, hey, there's a new file, and this is the name. So then inside, we're going to be using a convention for the file structure to decide what picture is that, what phone is that, and all of these things. Cool. So we have, for the buckets, we have everything solved. Meanwhile, on the hardware side of things, that I'm very happy not to partake, this Matt, one of our interns, and he wrote the first version of the sound structure. Matt is a very smart intern, and I think he's now a Googler. I'm not sure. He's trying to figure out what this lamp doesn't turn on. When I saw this, I thought it's like, it's mounted backwards. No, it's actually mounted correctly, but it is not plugged. So that is a problem. Yeah, took a little bit. He's still a very smart guy. He wrote really good code. This was our first version of Cloudspin. There's actually a previous version to this one. I could not find a picture of it. But before having tripods, we had selfie sticks. So we had 20 selfie sticks with phones on them. Really not stable. I do not recommend. Really, yeah. We did not break any of the phones, which is, I don't know how that happened. But yeah, so that was our first iteration of the processing. Back to the software side of things. So we have those notifications that are now being sent somewhere. We have to be able to handle them. How do we do it? Well, we need to be able to handle HTTP post requests. We saw that that's what we had. And we're going to need to decode that JSON file, that JSON object. We need to do authentication. And we're going to need to do authentication two ways. We're going to do authentication to make sure that the notification we're receiving is actually a notification we're receiving from the bucket, and not something that someone might have forged, which is something that we actually got. He was a Googler, but he was basically trolling us, and he did. So we decided to add authentication on that side. And also we need authentication to be able to communicate safely with the rest of our system. And we want that to be easy to do. And then we're going to need to also use task queues or push tasks, and we're going to see how those work in a minute. So we're going with App Engine. And why did we go with App Engine? Well, we need something that will be able to reply to HTTP requests. And that is what App Engine was made for. I'm very happy to write in Go, so all of those are written in Go. And Go is one of the languages supported by App Engine Classic. There's Java, PHP, Python, and Go. And it has a lot of constraints. You cannot spend more than 60 seconds to reply to the request, which totally fine with it. You cannot access the file system in the machine, totally fine with it. So awesome. On the good side of things is that I get to just send my code and forget about it. There's no DevOps. I don't choose how many machines or which machines should run this thing. And if for any reason I have a lot of traffic, it will just auto-scale directly. There's a lot of companies that use this. Khan Academy, Angry Birds, and all of these people that have very varied traffic, and you have traffic spikes. App Engine manages that very well for them. So we have two flavors, and they changed names not that long ago. They used to be called App Engine and Managed VMs, and now they're called App Engine Standard Environment, which is the one that I was talking about. You run in a sandbox, and everything is awesome as long as you match the constraints that we have. And then we have App Engine Flexible Environment. An App Engine Flexible Environment, it's basically give us a Docker container, and we'll run it for you. And this is really cool, because basically, all of a sudden, you have the good things about App Engine. It will scale as much as you need. It will not start as fast, because it's not a sandbox. It is a VM now. So your scaling will not be as fast as classic App Engine. So if you can do classic App Engine, I could still say go with standard environment. But if you need Go plus FFmpeg, for instance, which is an awesome library that doesn't run on standard environment, you could do it on a flexible environment. So we wrote a Go App Engine app, and now we're good. Except that we're missing the whole part that does things. So how do we manage the fact that, OK, I got a notification. I want to send it somewhere. I could send it to the machine that is doing the extraction of the frames. But what if that machine is down? What if there's many machines? Which one should I send it to? Do I need a load balancer? Kind of complicated. Instead, what I'm going to do is I'm going to use a messaging system, a synchronous messaging system. Why do I want that? Well, for availability, if all of my machines are down because I'm upgrading or maintaining or I broke it, things happen, I don't want people to get errors. I want them to just wait a couple more seconds till that new VM is up, and that will be able to handle that message. So that will actually absorb those problems. Also, if you have too much traffic, I don't want to DDoS my own machines. I want those messages to be there for a little bit longer. Yes, you will wait for a little bit longer, but my machines will not go down. And then also, if there's any outage, no one needs to see that, only me. On the other hand, there's better throughput. So if you have, imagine that you have all of a sudden 1 million videos that arrive at the same time. And I send 1 million requests to my 3 SAT machines. What will happen? Not a single video will be processed. All of the machines will go down. And the new ones will go down again. So sad state of things. Instead, with that messaging, I'm going to have a stable throughput, which is as much as machines can deal with, and then you wait. And then you have timeouts and things like that if you really want to say, oh, yeah, it took too long. So we're going to put 2 queues, one before the extractors and one before the stitchers. And we're going to be doing so we're going to need asynchronous messaging and also pull subscriptions. And why do we need pull subscriptions? First of all, what are pull subscriptions? Basically, pull subscriptions are the ones where I'm going to say, is there a new message? And then the queue is going to say, yes, there you go. And then I'm going to process it. And once I'm done, I'm going to say, hey, I'm done with it. If for any reason I fail or I forget to say, oh, I'm actually done, after a couple seconds, minutes, you choose, that task will be timed out and will be available on the queue again. So if for any reason your process fails, which happens, your task will still be processed later on. Push subscription, on the other hand, is I just send you a message and say, this is a new message, and then you have X amount of seconds to reply saying, OK, done. So we use Cloud PubSub. Cloud PubSub is exactly this. And why did we use PubSub? Because it's very flexible and very powerful. We're going to see in a minute how it actually works, but basically provides real-time communication, many-to-many, and completely decoupled. And this is something important for some experiments that we did later. So how does this work? Well, publishers send messages to topics. And then those topics have subscriptions, as many of them as you want. When I send a message to a topic, that topic will be sent once per subscription. So you can there multiply your messages. And then, for every subscription, you have a bunch of subscribers. And every message that gets to a subscription will be sent to one of the subscribers, which means that all of a sudden you can have one-to-one if you want, one-to-many as you choose. This is really powerful, because if you want to add more more topics or subscriptions, you don't need to tell neither the publishers or the subscribers. You can add things on top quite easily. You can use it from anywhere. There's a REST API. REST APIs are awesome. So you can use it from Go, from Android, from a Raspberry Pi, hidden under your bed, whatever you want to do. In our case, we use it in 2 places. We use it for the extraction topic, where we have a lot of extractors. And only one of those extractors will receive that message and process our video. And then all the extractors will send the extracted frames to the stitch topic. And then the stitcher will receive all those stitchers and at some point say, oh, I have all the frames for an animation. I'll just generate it now. So the fact that we had this allowed us to add extra weird stitchers. And we created this one where we have the beginning of one of the videos, then the jump, then the animation, and then the end of another video. So this starts to look a little bit more like The Matrix, which was really cool. I totally forgot his name, but he was helping us recording a video, and he was super excited about this. It was lots of fun. OK, so now we have pipeline processing. So we have everything is already done. We're just missing doing the thing itself, extracting the frame, so detecting the audio peak and extracting the frame, and then stitching all the images together to generate that image. So how do we do this? So Matt, our dear intern, wrote some code that did exactly this. And I just modified it a little bit to be able to basically get files from Google Cloud Storage, process the video, and then put it back to Cloud Storage again. This is the whole code for the frame extraction. And the important thing about this is that this is the code that I modified. Git blame says so. So there's a bug in this code, and it's mine. And I'm using standard deviation instead of mean for the noise. And this is basically, instead of getting the mean power of the sound on a frame, I'm getting the standard deviation of the power on a frame. And this works as long as the room is silent, which is why the night before the demo, Ray and I are trying to figure out at the venue at 1 a.m. what is going on. Till we actually figured out that that standard deviation was just silly, and it was instead mean. We changed one function call, and then we were all happy again. Yay! That was pretty intense. Then we modified it to move to, instead of getting something with standard deviation and very complex stuff, we just compute how much noisy a single frame is, and we choose the noisiest one. And that single algorithm just works. So what do we need to do to process these things? Well, we need something that is going to be using FFmpeg to do audio processing. MoviePy is actually a library, Python library that is a port. No, not a port. I forgot the word. Whatever. It actually calls behind FFmpeg. We're going to need to use PubSub again. And we're going to need this to work really quick. We use Google Compute Engine. Why? Well, we want something that is going to be running continuously. And that's not App Engine. App Engine is for something that replies to requests. We want something that will start the process of going to PubSub and say, give me one new task. So we use Compute Engine. We have Compute Engine everywhere in the world. It's very fast, and it's very affordable. Then on top of that, you can actually choose what kind of machine you want. So you could say, I want a machine with 32 cores and 208 gigabytes of RAM. And we have that. But maybe you want to spend less. And it's like, I want I think it's G1 micro, which is like a piece of a processor somewhere. And it's less than 1 cent per hour. It's like super, super cheap. And that's totally fine. And we have those too. And then also you can choose whatever you feel like. So basically, you have sliders and choose more memory, more CPU, less. I'm going to go quite quick on this one. But basically, what we did was, OK, so I want a bunch of machines to be running. And I want those machines to be managed somehow. So I'm going to create this managed instance group. And a managed instance group, it's just a group that is managed of instances, as the name implies. And they're all exactly the same, except for metadata. The metadata is the only thing that you can change, but they run exactly the same software, exactly the same hardware, same OS, all of those things the same. Then you have the instance group manager. And this is the one that is going to add or remove instances as we need. And this allows us to have load balancing, autoscaling. Then we need an instance template. And the instance template is basically, OK, I need one more machine. Give me the recipe for it. So, you're going to run an Ubuntu machine with 32 cores and all those things. And this is the startup script. You can totally do that. It's very simple to do. And if you have a Neo template, you can always say, hey, this is the new template. Please do a rolling update. And it will just restart regularly those machines, one after the other, to make sure that after a while, you have all of your machines, all of your fleet is running the new software. So that's pretty cool. So you end up with something which is kind of complex. But we actually did this at the beginning. And since I'm a very special person, I decided, no. This has to run on Docker. Because, come on, Docker. So what I did is like, I'm just going to create a Docker container for this teacher and a Docker container for the Extractor. And now what I'm doing is every single time I start one VM, it's going to be running CoreOS, because CoreOS runs Docker by default. I don't have to install anything. And then the startup script is Docker run my container. And it works, which is really cool. So we got started. And then we have 20 machines running just to manage this load, which is kind of ridiculous. Because we're running on the old world, right? We're not on this old world where you have one machine and a bunch of applications on it, but we're on right after. We have a bunch of virtual machines running on every single machine, and every application runs inside of its virtual machine. They're kind of slow. There's a lot of resources that are wasted because you're replicating many of the things that every single machine is using. But since I'm using Docker, one could think, well, you're using containers. Why don't you put all the containers inside of a single virtual machine? And I decided that that was a good idea. So we started doing that. And then it's like, OK, how many do I want to put in there? Do I want to put 4, 5? No idea. So as soon as you start having many containers, the next step is container orchestration. So we went to Google Container Engine. And this is what Google Container Engine looks like, which is exactly what we had built from the beginning. But now this is automated, and you don't have to manage it by yourself, which is awesome. And basically, everything you need to do is you say, hey, I want a cluster. My cluster is going to have 5 machines. These are the kind of machines. And I want to run 20 of these containers. Run them wherever you feel like. And if one of the machines goes down, don't even tell me. Just move it away. Restart that machine later on, because there's an instance group manager. And all of those things work automatically. So I like to think about it as, if you have compute engine, which is the part where you have a lot of flexibility, but also DevOps, and you have App Engine, where you have no DevOps, but not as much flexibility, I like to think that Container Engine is kind of up there, where you have all the flexibility you want, because it's a container, and you can run whatever you want in it. But at the same time, you have less DevOps to do, because you have all of the Container Engine and Kubernetes helping you orchestrate all of those tasks, which is a pretty sweet world. So yeah, Google Container Engine. And I'm almost running out of time. But that's what we got, around 3 times resource increase, which is pretty good. At this point, we had spent enough money on tripods that this was not that important anymore. But still, our manager was happy for this. So the whole architecture, we have all our files are stored in Google Cloud Storage. We use App Engine to process our notifications, PubSub to manage all the tasks and smooth the workload, and then Container Engine to actually track those tasks. Time for a fun story. We did this also in Tokyo. And we just sent the whole specifications of, these are all the cables we need to Tokyo, and then people in Tokyo bought them. And I was like, so the phone, to be able to detect the audio, we need this specific cable. This is a TRRS to TRRS thing. Because we tried to make them ourselves, and this is how it looked, super pro. And this didn't work. So we went, let's use off-the-shelf. Much better, Google style. Let's use cheap off-the-shelf components that we can reuse if they break. So what we did is, OK, we have the control tablet. We press the button. There's a cable that goes to an amp. Then that amp sends 4 cables. Every single one has a hub. And then that's 20 phones. Boom, done. Yeah, doesn't work. Because you need that cable. It's a TRRS to TRRS adapter. And what happens if you don't have it, which happened in Tokyo? Well, you go to the Google makerspace in the Tokyo office, you find a bunch of resistors, and you spend the night soldering, making those amazing-looking cables. And the demo actually worked. That was lots of fun. So in conclusion, I just have a couple seconds to finish. We were able to build, in around 2 weeks, a demo that, hardware-wise, yeah, it was, it worked. But software-wise, it's very robust. It was very easy to build. It's actually very effective to run. Whenever it's not running, the Autoscaler just shuts down everything. So there's no cost according to it other than the storage. And it was lots of fun. So thank you for all the demo builders, or for the team building it and throwing plushes in the air. There's a gopher there. Thank you very much.